Okay, so I'm going to give a quick background story to how this project on Stop Random Walks came about. And just to get us all on the same page, this is the impact of climate change, anthropogenic climate change on the Northern Hemisphere temperature record. I pulled this from Crew a little while ago. And as you can see, this is the temperature anomaly, anomalized to the 1960s to 1990 period. So we have had significant warming of about approaching over 1.5 degrees Celsius already in the Northern Hemisphere relative to that baseline, which already has some warming. And what has shifted with this and been heavily reported now over the last 20 years is that as we have this period of warming, especially emphasized and obvious with kind of a trend towards much warmer temperatures in the last 40 years, since about 1980 is a common inflection point people talk about. A lot of phenology has gotten earlier. So a lot of the timing of biological events has moved and shifted earlier. This is one I have studied a lot. Harvest records from wine grapes averaged across France and again anomalized to September 1st here. So going all the way back to the 1600s, these records go back even further. You can see that linear dive towards earlier dates that have happened since 1980 is really an outlier, even in some of our longest data sets from the cause of anthropogenic warming. So as Krishna mentioned, I study phenology, which is the timing of major growth and reproductive events of organisms. It's things like when birds arrive on their nesting grounds, but it's also things like the timing of flowering, leafing, fruiting, which I focus a lot on since I think a lot about plant communities. It is impressively important how much we're going to be able to forecast, adapt, and mitigate the impacts of climate change. Certainly, one of the things I think about a lot now is the idea that we tend to assume that as growing seasons in forests get longer, those forests will sequester more carbon for us because they have more time to grow. That's a big open question, but that is one of our fundamental assumptions when we project forward how much climate change we'll have. We assume something about how phenology will shift and what those impacts in turn will be on how much climate change we will get. There's other big impacts on things like trophic mismatch, and how badly wine grapes, for example, are impacted by frost or heat really depends on phenology as well, which I could give a whole other talk on. But whether or not we continue to have this advancing phenology has become a really big question over about the past 8 years. It started with this paper that came out in 2015 and suggested that the advances that we had been seeing, because we had been reporting at that point about 10 to 15 years of advances in most phenological events, especially plant events, and most especially spring events, which had tended to advance 2 to 3 weeks in the Northern Hemisphere at least. We were starting to see what looked like a slowdown in those advances. This came out as a big paper in Nature, and various versions of this have been published in all sorts of journals over the last 8 years. The idea that there is some sort of weakening response of plant phenology, things like leaf out, flowering, spring flowering, to the increasing warm temperatures. So somehow we're not getting as big an advance as we used to get in leaf out per degree warming. In the recent years, basically the last 10 to 15 years, we've started to see this slowdown or this stall. I want to show you what the data underlying these papers looked like, because it's what I was staring at before I started working on this project with Jonathan Auerbach. And so these are data coming out of Europe for Betula pendula, which is a tree that's common across Europe, silver birch. And I've pulled out just 45 different sites of data so that I'm looking at the exact same sites on the bottom graph as the top graph. Day of leaf out of the tree is on the vertical axis, and the mean spring temperature in a 3-month window, I believe, is on the horizontal axis. The top panel is the 1950s. You can see the average temperature is about 6 degrees, and I fit a linear regression. So just change in days per degree Celsius is the slope here. To each different site. And hopefully you can see that these slopes look much steeper, or importantly steeper, than the slopes you see below, which are from 2000 to 2010. So after the 1980s significant onset of increasing warming from anthropogenic climate change. Here, the average temperature is around 7. And obviously, you can hopefully see that for most sites, the slope has gotten much shallower. In fact, if you take the average, in the 1950s, we would have said you were getting an advance of about 4.3 days of change in leaf out per degree Celsius of warming, whereas in the 2000s, you were seeing about 3.6 earlier days of leaf out per degree warming. And this is the concern that has been reported over the last 8 years. What is going on here? We had actually predicted this in my field of plant phenology because we know that bud burst date, which I'm showing at the sort of right end of your panel, is dependent on a process that starts in the fall. So most temperate plants, especially woody trees, enter dormancy. This starts sometime in September to October in most of the Northern Hemisphere temperate growing regions. And plants go into a phase called endodormancy, where, as best we understand, they need to accumulate a certain amount of winter cold. So they're basically accumulating more and more winter cool temperatures to help them thermosense how long the winter has been. And then once they sense that the winter has been long enough that they are hopefully past the period of cold, they then switch to being responsive to warm spring temperatures. And we call this forcing, with the idea that the plants are being pushed towards an event. And they're also ecodormant at this point. So they are able to respond to the external cue of warm spring temperatures. And those spring warm temperatures, that forcing also, at that point, we also assume that day length matters from a series of experiments we've been doing for over 80 to 100 years that show plants will leaf out a little faster if you give them a longer day length in the spring. So this whole sequence of events means that though we focus on spring warming or forcing in my field, we knew biologically that plants have these other cues. And so we might simplify our story as we had been in the periods of, I would say, like the 2000s onward. We had a very simple story where you could look at leaf out, the phenological response here on the vertical axis. And you could say, okay, currently this is the linear regression we're seeing. We'll project it forward, but that assumed a really simple model where just spring temperatures or forcing mattered. And we knew that somewhere we might expect this slowdown because if the plants don't have long enough day length for how warm it is, or the winters have warmed up so they don't actually get the sufficient chill before they get a really dominant spring forcing cue, then we expected them to start to stall out, which is exactly what we had seen. So this sort of slowdown in the phenological response. So this paper I actually published in 2014, and the big paper about declining sensitivities came out the next year. There was a huge debate and still has been about what drives this. Is it winter chilling as the other cue? Is it day length? The debate has gone on and on. My lab worked on it extensively. We had a paper come out in 2020, and we looked at what those forecasts would actually predict compared to what we were finding for models of forcing, chilling, and including both of those. And I could go into great detail, but I will basically say that we found no evidence actually that increasing or lower chilling or even changes in day length should actually be driving this sort of declining sensitivity that was being observed and that we were are very concerned about in terms of leaf out for forests. What's going on? Well, what happened then for my lab is we went back to the drawing board. We pulled together the analyses we had done. We wrote a paper saying, you can't match up what we actually observe in experiments and observations with the observations we're seeing in the data on the ground in Europe. So we went back to looking at this. I sat down and did something I probably could have done 5 years earlier, and I constantly encourage people to do, which is actually simulate your data. So I simulated a really simple model from the story I told you about endodormancy and ecodormancy, but I deleted out all of the interesting processes from chilling and day length. So I said, what if leaf out doesn't rely on winter cold temperatures and it doesn't rely on day length? What if it just relies on thermal sum? That sort of simple story we tell ourselves. But the simple story is actually that plants are accumulating thermal sum. So it's not that one day is 10 degrees and they leaf out. It's that over the period of the spring, it's 10 degrees one day, 8 degrees the next day, 15 degrees. And eventually that thermal heat sum, that forcing that adds up, leads the plant to cross the threshold and leads to the phenological event of leaf out. So I simply simulated a very simple thermal sum model where everyday temperatures occur. If they're over some baseline temperature, the plant is experiencing them and accumulating them as a threshold towards the event. And I did it across different temperatures. And then I looked at what the simulations predicted. So in this case, estimated sensitivity means that plants have a larger response as you go from top to bottom of the vertical axis, a little bit counterintuitive. So I put declining sensitivity on the right side. Declining sensitivity is going to happen as values go up towards smaller negative numbers, those are smaller responses. And I simulated a very small amount of warming, the amount we've seen. So we've seen about 1.5 degrees in the northern hemisphere. I simulated from 0 to 1, which is on the horizontal, or 0 to 2, which is on the horizontal axis. These are what my simulations looked like. Again, a super simple model, forcing only, no photoperiod, no chilling, and they predicted this decline. In fact, I could put that silver birch data I showed you at the beginning from Europe on top. So the 1950s estimate is on the 0 degree warming mark. And then there's been about a degree of warming by the 2000s. So the 2000 to 2010 value is shown there too. And they line up remarkably well in terms of predicting the observed response, but again, requiring no chilling, no forcing, no complex biological response as we were expecting. So what's happening? I took this problem and I took my simulated code and I met Jonathan Auerbach, or I'd met him before, but I was chatting with him, I think in 2019 in New York about my problem and showing him my simulated data. And that led to what he'll tell you about, which is all the interesting statistics and biology embedded in the cool statistical problem right now. So I'll pass it off to Jonathan.
Thanks, Lizzie. I apologize. I'm a little sick from the Thanksgiving break, so I'm gonna feel free to interrupt. I also apologize that after listening to the introduction, there's no package here per se, but I think hopefully a useful explanation of the problem that Lizzie brought up and some demonstrations using R and STAN. So I apologize if it's a little different than what's usually done. Let me make this full screen. I put there's an HTML file in the repo, which is the slides that was generated from Quarto, so you can unwrap the code or whatever. And then I also put in a PDF version if anyone wants to follow along. There's also an R code file, and then the STAN files and everything. Everything in these slides is separated. So full screen. And also I should also apologize. I'm not a biologist, not an ecologist. So if I use words incorrectly, feel free to correct me. That's on me. But I want to learn. So if I use words incorrectly, please let me know. So as I was saying before, Lizzie came to New York with this observation, and it turned out after some kind of discussion that this was what she was observing was just a natural consequence of what we would call maybe in statistics the central limit theorem for stopped random walks. And so I'm going to very, very briefly show you some theory, hopefully kept to a minimum, and then show how we can use that theory using LM, GLMs, and STAN in order to model the type of phenomena that Lizzie was seeing. So first, I'll review the CLT for stopped random walks. Then I'm going to go through application 1, which was some experimental data from Charrier et al. And then I'll go to application 2, which is observational data from Marsham, who I gather is the father of phenology, and show the model kind of fits equally well with some caveats. And then CLT is not always appropriate. It relies on an asymptotic approximation. So I'll briefly review a non-asymptotic model for stopped random walks. And I might keep it maybe a little high level and point out, not go through the code in detail, but point out highlights. And then feel free to email me or write in the chat or whatever if you need clarifications. Again, hopefully this is useful for some of you that maybe you have stopped random walks you're looking at and could use the theory to help analyze it. All right, stopped random walks. So let me hide this bar. So many biological processes can be modeled as stopped random walks. And so what I think of in the back of my head is something called the law of the flowering plants, which basically states, the law states that a flower first blooms in the spring after cumulative temperatures reach a threshold. So it was first observed by Raymer in 1735. It was extensively studied by Quetelet in 1846. I wrote a very brief blog post about it, which I'll include in the references at the end. And it's really exciting to statisticians because Quetelet was such a formative, force in modern day statistics. So that's why we as statisticians really like this law. What I'm told is in biology, this is known as the growing degree day model or ecology, in which temperature is thought to exert a force on a plant. And then when after the plant experiences enough forcing, it blooms or leaves out or whatever. And apparently explains a lot of processes in biology, leaf out, insect emergence. From a statistical standpoint, a cumulative sum is a random walk, right? If you're summing a bunch of random things, it's a random walk, possibly with drift. And the walk stops when the threshold is passed. So that's why we call it a stopped random walk. Go back to the slides here. So here is a simulation. Let me just, I guess I'll describe the image first, and then I'll briefly highlight what's going on in the code. So here, we're assuming that this flower, say, wakes up in February. It starts accumulating ambient temperature. So this is cumulative temperatures here. And then after it gets about 300 degrees Celsius, it, say, first blooms, and that's early March, or maybe right before March starts. So the end of February. All I'm doing here is to simulate the data as I'm drawing from a normal distribution for 121 days from January 1st to April 30th. And then I'm just determining the bloom date as the first day the cumulative temperature exceeds 300. And then I just plotted it here using ggplot, which I assume a lot of people here are familiar with it. Again, the code is in the R file. In order to study these types of processes, we're going to just, set some notation so we can state two main assumptions. And we're going to let xi denote the force exerted on a plant from day I. And we're going to assume the xi are, say, follow some distribution where the mean of the xi is the ambient temperature, mu. And we're also going to assume the xi are independent with a common variance sigma squared. All of these assumptions can be relaxed. Typically, the ambient temperature, especially in observational studies, maybe in an experiment, you can fix it at some temperature, but typically they vary. And so you can allow the ambient temperature to vary over time, but in order to use this theory, the sum of the mu I can't grow too quickly. So we would say it's regularly varying with index 1. So basically, asymptotically, or when the number of days is large, it's as if it wasn't really varying. And so the CLT for stopped random walks is very simple. We would denote the cumulative sum using S, where we're just looking at the cumulative sum of temperatures from day A, before it was February 1st, until I. And we want to let the bloom date n sub gamma to be the first day the sum of the temperatures exceeds gamma. So that's how we notate it here. And the central limit theorem for stopped random walks just says that when gamma is large enough, the bloom day is roughly normal, with mean gamma over mu, plus A, which we remember was the start date, and variance, gamma times sigma squared divided by mu cubed. Maybe it looks a little bit kind of complicated, but is actually, look at it for a little bit, is not too bad. Note that typically in the central limit theorem, you let n, the number of observations, go to infinity. In this case, we're letting the threshold get large. As the threshold gets large, it requires more and more days to exceed the threshold, and that's what's driving the central limit theorem-like result. So going back to the simulation from before I just simulated one day, now we could simulate many, many days and see if the approximation works out. So here I just created a simulation function where I'm going to simulate again 121 days, norm distributed about some mean temperature with standard deviation 5. I guess there's a question. I don't know if someone can... I don't know if do I call on someone?
No,
Sorry.
you go ahead. Keep going, and I'll check in.
Okay, great. Okay, yeah. So that's temperatures normally distributed with some mean and variance from January 1st to April 30th. And again, we're just going to say the temperature blooms the plant blooms when the cumulative temperatures exceeds 300. And we'll just simulate for a bunch of different temperature thresholds, say from 5 to 25. And so the data this is the first two observations, but it kind of looks like this. Here are different bloom dates. So for the first observation, it exceeded the threshold on March 25th. And that was when the ambient temperature was 5 degrees Celsius. And then for another observation, it exceeded the threshold on February 28th. And that's with a mean temperature of 10. And you'll notice that if the bloom date is roughly normally distributed, we can just fit this, because mu is observed, that's the ambient temperature, we can just fit this using linear regression, which is what we'll do here. We're just going to fit it using linear regression, where the x variable is going to be 1 over the mean temperature. And we just have to recall that the variance changes with x. So we have to put in this mean temperature cubed. But if we do that, we simulated with a start day of 31. I think this is actually 32. It was February 1st. And a gamma of 300. So this should be 32. But basically, you fit linear regression, you get back the results. The start date was 32 and gamma was 300. Okay, and then I promised last slide with math. Hopefully not much more math. Maybe one more slide with math after this. All right, Bloom dates. What central theorem for stop random walk tells us it's normally distributed with mean gamma divided by mu, the threshold divided by the ambient temperature, plus the start date, and the variance is equal to gamma times sigma squared divided by mu cubed. The things that are important to note is that the number of days till bloom, n minus a, is inversely proportional to mu. And that actually explains the declining sensitivity that Lizzie was observing in her data. And also the variance is also proportional to 1 over mu cubed. That's going to be an important consideration when we start fitting data, as I'll show you in a second. And so gamma here depends on the temperature scale. So if we used Fahrenheit instead of Celsius, then gamma would change accordingly. So gamma is really only identified if mu is known. And then the last thing I'll say is we don't really need to know the start date. And in fact, we don't need to know the day that the plant starts accumulating temperatures. And in fact, it can be any day. We could start counting January 1st. We could start counting February 1st. It doesn't really matter. And then it's just, we're still going to have a normal distribution with just a different kind of intercept. That's another takeaway. So now we can start fitting some data. I'm going to aim, I guess, try to get done with this by hopefully 1 p.m., maybe answer some questions. If somebody has questions, maybe I saw some in the chat or something, feel free. I'm not monitoring the chat, so feel free to ask them and feel free to interrupt. Okay, we're going to look at experimental data. We're going to look at this Charrier et al. 2000 data from Charrier et al. Published in 2011. We're going to look at 30 walnut trees, juglans. I don't know how to pronounce it. I apologize. They should really be italicized. And they looked at 6 different genotypes at 2 locations. And what they did was they cut stems from each tree into 7-centimeter long pieces with 1 bud at the end. So I guess there was a stick with a bud at the end. And then they chilled them to 4 degrees Celsius and then forced them. And so because of how the experiment was designed, they kind of knew when the forcing period began, when the temperature started accumulating from the perspective of the plant. And they did this at the same kind of temperature range that we just simulated. They looked at 5, 10, 15 degrees, etc. And so we're going to look at the relationship between 2 variables that they collected. One is force temp, the temperature during forcing, these temperatures. And the other is response time, how long it took for the bud to burst. They define it as when 50% of buds had unfolded across all of these, I guess, sticks that they cut. And so this is what the data looks like. Here are the different temperatures, and here are the response times. And if you were following along, you could just read it. It's this DWSL data set that was provided to me by Lizzie. Thank you, Lizzie. And we're looking at data set Charrier 11 and this experiment 2. And this here just creates the table. And this is, if you plot the data, this is what it looks like. We're just using ggplot here. So we're going to take this Charrier et al. Data set. We're going to use ggplot and plot. We're just plotting the force against time. So here we have the temperature degrees Celsius, the ambient temperature. And here we have the average time across all buds until bud burst. And so this was we can fit the linear regression model from before. It seems to fit the data really well. Again, you see this kind of declining sensitivity. Those temperatures increase. The small degree change in temperature has a decreasing effect. The magnitude of the effect is smaller. The mean time till bud burst. And you'll notice here there's much larger variance here. The variance is much smaller here. That's the fact before I was showing you that under the theory, the variance is inversely proportional to the ambient temperature cubed. And so you expect huge variances here in the data. What that means from a statistic standpoint when you're fitting the model is that the model is not going to actually spend a lot of time trying to fit data here. It's going to actually really care about the fit here because this is relatively more noisy. It's going to hold less weight in the model. And so anyway, we have the same ggplot from before. In order to fit the linear regression, we're just going to use geom smooth method LM. And we have to make sure 2 things, that we model the mean bud burst time as inversely proportional to temperature, and that we allow the variance to be proportional to temperature cubed. Really, well, it's not the variance, it's 1 over the variance. The weights are 1 over the variances in weighted least squares. Another thing you can do is you can actually fit a generalized linear model. It's a slightly different model, it's a slightly different equation, but yields pretty much the same results. In this case, y is inversely proportional to 1 over x as before, but we're actually going to use the inverse Gaussian distribution, not because it follows inverse Gaussian distribution, although if you've studied stopped random walks, you know that the work that Wall did, he derived the inverse Gaussian as the limiting distribution. But we're going to use it because it actually provides the right variance term. It's the right this family distribution. When you're fitting GLMs, all that really matters is the link function and the variance. And so this is going to give us the right variance term. We're going to use link identity though. I think the natural is I want to say inverse or inverse squared or something like that. Anyway, that's what this fit looks. It looks similar. It's a little bit lower. And then the third way to fit it is using Stan. And Stan is great. It's a little harder to set up. You got to put in the parameters here, but then we can type the formula directly in to Stan. So remember we said y, which in this case is going to be the average bloom date, is going to be normally distributed with mean gamma over mu, threshold over ambient temperature. Obviously the threshold is unknown. We observe the ambient temperature plus delta, which is the difference between when we started counting and when the plant started accumulating temperatures. And then this was the variance, was gamma times sigma squared divided by mu cubed. And then we can also generate our predictions in Stan as well. So the R code here in order to create this plot with Stan is we're just going to load our Stan. We'll ask it to use multiple cores. I commented this out because for Quarto, how I coded this, it automatically reads this Stan code in. But if you were running this in RR Studio, you would just load in the Stan model, and then you would use sampling to sample from it. We're just going to input the data as you would any, the linear model or GLM. And just Stan isn't a default for ggplot, so we're just going to add the uncertainty bars using G on ribbon as the posterior means from Stan, or from the predictions from Stan, and then this is the lower and upper quantiles to get a 95% interval. And so you could say, whereas previously using GLM or LM was a little bit higher, for Stan it's a little bit lower, and the uncertainty is larger. These are uncertainty intervals on the predictions. These aren't predictive distributions. If you're going to do that, then if you were running Stan, you'd want to put something in the prediction. You want to draw from a normal distribution with this variance, and that would give you predictions. So maybe before going on, maybe I should stop real quick, see if anyone has questions or... Everyone's good? All right, great. Not a mad rush for the exit. All right. Then I will, all right, continue. All right, okay, so that was fitting experimental data. We're going to have to complicate the model a little bit for observational data, as I'll explain in a second. So again, we're going to look at data from Marsham. This is a data set that goes from 1746 almost till modern day, 1958. And was started by Robert Marsham. Again, as I said before, my understanding is he's the father of modern phenology, who I guess just went outside and started recording in his notebook 27 signs of spring each year. And so the Marsham family continued to collect the data after his death. This says 1979. I think that should be 1797. I think I was dyslexic for a second. I'm going to look, or today we'll look at the day that Marsham first noticed leaves to appear on his oak trees. And so we're going to get the spring temperature from, I think, nearby area. It's the ambient temperature nearby. Before, we don't know. Again, before in the experimental setting, ambient temperatures were fixed at some number. Here they fluctuate daily. But we're going to assume that the fluctuations that on average it's relatively not changing too much between February 1st and April 30th. And we'll see, I'll give it kind of a brief justification in a second why we can do this. And then we're going to look at the response time, which is the number of days from January 1st until bud burst. And note that our setting is different here primarily in that the day in which the plants start accumulating temperature could change each year. And so before we fix it across experimental settings, today we're going to let it vary, or in this setting we'll let it vary. And so this is what the data looks like for different years. We see the response time, which is how many days from January 1st it took for the oak tree to first leaf. And then we're going to see the cumulative temperature, again, between that fixed date of February 1st, the end of April. And so it's changing over time. And so if you're following along, you would just read the Marsh and Combs data set. Again, provided to me by Lizzie, thank you. And we're going to be looking at oaks. And the temperature is going to come from a separate data set, which has the daily temperatures from 1772 until present day near the area. We're just going to join the two to create our data set, and we'll view them here. And here I'm just showing 4 of the observations in the table. And so this is what the data set looks like. We see cumulative temperatures. Before you saw what was like kind of average temperatures. Here we're seeing cumulative temperatures now. And then on the y-axis, you're seeing the time from January 1st until bud burst. A number of days after January 1st, but it's pretty much the same plot that we made before. You can see it's basically the same code. It's the same ggplot code. I'm just going to run the same exact code as before. We're going to use geom smooth. We'll do LM and GLM, 2 different ways of basically fitting the same model. They're not the same model, but they're very similar. Different ways of accounting for the fact that the variance doesn't equal the mean. And you can see them here, and you can see the same kind of curve declining sensitivities data that here when temperatures are lower, there's the marginal change in temperature yields a much sharper change in time until bloom. And then towards the end, it basically becomes flat. That a marginal change in temperature doesn't really change much. The problem with this is that this assumes the start date A is basically the intercept in these formulas. That the gamma is the coefficient in front of 1 over x, and the start date is A. And so that's a problem. We're not really taking into account the fact that the start date could vary each year. And so one way we may do that is using Stan. Again, it's the same exact model as before, where y is going to be normal with mean gamma over mu plus delta, and variance gamma times sigma squared over mu cubed. But then we're going to add a variance term. We're going to have basically a random effect for each year, which we're going to assume is normally distributed and independent. So we can just add the variances. It's got mean 0, and we're just going to add them. And so in this case, it's the variance, I guess, is tau squared. So the tau is the standard deviation. We just add them. And basically, what happens is that our mean is changing. Basically, the start date changes so that it fills up the data. This width here from the previous kind of uncertainty interval, this width here just reflects the uncertainty in the start date each year. But otherwise, we have the same fit. And you can see here before, it's the same code to fit. We're going to load Stan here. Load the Stan code, which is in the directory, and then we'll run Stan before using the sampling command, and then it's the same because it's not in ggplot. We're going to make the intervals using geom ribbon. Great. Okay, so maybe I'll pause because I was going to end in the next 10-15 minutes by kind of talking about what happens if the asymptotics fails. So I don't know if there's any questions. Anybody, maybe a good time to pause. I guess everyone's feverishly following along, so I'll keep going. Great. So seeing that there are no questions, I'll just kind of end by talking about what a non-asymptotic model might look like. So what if the the model relies on the fact that the threshold for the plant is like arbitrarily large. That the oak tree you're looking at has a very, very high amount of temperature needed to bloom, and so you're summing up a lot of kind of independently distributed temperatures to get to that amount, which is kind of what gets you this Hengel limit theorem. So what if that's not true? Well, then you could do a non-asymptotic model. You could throw it in Stan, and just have to make different assumptions. So as I was saying, uh, maybe before that, kind of, I had some one note about a takeaway. Well, you guys can read this at your leisure. This is just saying why was it in the previous slides it was okay to just use the cumulative temperature between February 1st and April 30th instead of knowing the actual ambient temperature between the start date and the bloom date. And basically, when you're summing a lot of temperatures, if you're off by a little bit, it doesn't really matter, is the argument down here. I'll just talk about what a non-asymptotic model might look like. I apologize, I'm a little cut off here. Let's see if I can fix that real quick. I'm just going to leave it. I guess you can see it in the slides. It basically just this thing is just looks like this using n-1 instead of n. So for a non-asymptotic model, we're going to have to kind of get our uncertainty somewhere else. So we're going to assume that instead of relying on the fact that some of the xi are asymptotically normal, we're going to use the fact we're just going to assume that the temperatures, basically, that the force experienced by the plant is normal with ambient temperature mu I and variance sigma squared. So we'll just assume the observations are normal, and we'll use this kind of trick, I guess, this relationship that the CDF of the bloom date, the fact that probably the bloom happens before some date m, is basically the same as the probability the random walk has exceeded the threshold gamma. And we know this because we're assuming the S's are normally distributed. We can write this using the cumulative normal distribution. So it looks like this after accounting for the mean and the variance. Since we know the CDF of n, we can just write out the likelihood, and it looks like this. And the only kind of, I guess, the only trick is that now, if I'm going to throw this in Stan, for example, I have the sum. I basically have a discrete parameter a, which is going to tell me when do I start summing the mu's, the ambient temperatures from a to n. Stan doesn't like discrete parameters. And so I'll just use this little trick, which is very, very common in Stan, where you write like a discrete parameter. You relax. This is an indicator function. You relax it using the logistic function. And so this allows a to be continuous. And so we can write a discrete sum using a continuous function of a and let a be continuous. All right, so what does the Stan code look like? Well, it's really simple. We're just gonna copy and paste this likelihood into this before we have the normal distribution, the asymptotically derived. We're just gonna copy and paste it right here. And we're gonna increment the log likelihood by the log of likelihood. Obviously, we're gonna increment the target by the log likelihood, which I just derived in the previous one, using basically the normal approximation. And then prediction is easy. We're just going to predict once we, know gamma, have a posterior distribution on gamma and delta. We're just going to use it to predict new observations. And now A is treated in the Charrier. We're going to not treat A as random. We're going to have one fixed A with fixed starting date, and then later we'll let A be random for the observational. And so as before, we're just going to run this model Stan3, Stan mod 3, going to fit use sampling. And then we're going to use ggplot, and we'll have a geom ribbon for the uncertainty intervals. And that's what it looks like here. And actually, it fits these tails, these here, much better than the previous Stans did. And so before, this is what the model looked like with the asymptotic, with the approximation. And so to me, this looks a lot better. If we want to modify this for the Marsham data, we're now going to have a different A for each year, and we're going to let A vary according to a normal distribution. So this was the same likelihood as before, and now we're just going to let A be normally distributed. And it's a little complicated. We basically have to build out the temperature sum, in this case, using a double for loop. And so if you try to run this on your computer, it might take a little while. I probably, in these slides, so that it would not take too long to compile the slides, I probably had it stop after only a few thousand iterations. It's probably run much longer to make sure that the chains, they probably converge, but could converge a lot better. I don't think the results change, though, in running the two models. And as before, this is now going to be Stan mod 4. We're going to build out this temperature matrix and just throw it into Stan. And as before, we'll make our ggplot again using geom ribbon, and the fit will be the geom line. And this is what it looks like. It's basically determining the curving uncertainty here on the data where the variance of the data is the smallest. And then up here, because of as I said, one over the fact that the variance of the data fluctuates a lot more when temperatures are small, this data is going to be less informative of this trend. And so that's why it kind of looks like this. Maybe we might say it's a worse fit, and maybe the asymptotic approximation was better. So this model might not be a good idea if the xi are say normally distributed, but there's some covariant structure. It's maybe temperatures are autoregressive, and then maybe you would want to account for that autoregression. You'd account for it down here in the variance. And that could be why maybe the asymptotic works fine, but this finite sample model maybe is violated. And that autocorrelation could be especially pronounced when cumulative daily temperatures are small, because there aren't that many days being summed to reach. I guess it's the opposite. These are fewer days being reached. So I don't know, maybe something about the autoregressive nature of the data is causing some problem here. Okay, so I will briefly conclude, and then I'm happy to go back or answer questions. So I wanted to end just by comparing the different models, fit 1 through fit 4. So code's a little ugly, but basically for each model, fit 1, 3, 2, 4, all these different models, I'm going to extract the estimates of gamma with the threshold. So for all 4 models, and I'll get the lower 25%, the lower 2.5%, and the upper 2.5%, so 95% uncertainty intervals. I'll make a table. And so for the experimental data, the Charrier data et al., 2011, they both models produce a similar gamma. The asymptotic one says, it's about 750. This says about 1,000. But if you look at the uncertainty intervals, they pretty much overlap. Here, the Martian data, the two disagree. This says 250. This says, 350, 400. The intervals don't overlap. Maybe in this non-asymptotic model, which made the normality assumption, if you allowed for autocorrelated temperatures or something like that, then the intervals would overlap and the two would agree. Or maybe it's a violation of the asymptotic assumptions and that this model shouldn't be used. So just to summarize, I know it's a lot, but what do? We justified modeling biological processes as stopped random walks. So the first thing I did was review the CLT for stopped random walks. It looks like the regular CLT, but now it's instead of the sum being normally distributed, it's the day that the sum first exceeds a threshold, or the Bloom date that's normally distributed. And I applied it to experimental and observational. We applied it to experimental and observational data. And so we found, in general, I think, if you may feel differently, that the CLT approximation compared well to the non-asymptotic model. And of course, we can always complicate these models by allowing more covariance and additional variation. If you had different species, of course, you could use the mixed model, or you can, have separate, random variables. We could have thrown in we could have done you can't do the normal distribution for the inverse Gaussian. We could have thrown in a different start date for each year and had a random effect. So it'd been a mixed model. And these are just the 3 references I noted.
Fantastic. Thank you, Jonathan, and thank you, Lizzie. That was excellent. Really appreciate everything you put together here. I'm going to open it up for questions. So again, if you have a question, put it into the FE 2024 poll. And so the first question here it says, thanks for the presentation. Could you elaborate on how STAN differs from other methods? What are the upsides and downsides?
I guess I can answer that since I was the one who showed stand code. Um, how does stand differ? It's a different objective function. It's estimating. It's a different. I mean, ultimately, you have two kind of frequent distant Bayesian statistics. They are estimating different things. They're different notions of uncertainty. From a maybe computational standpoint, from your Stan has perhaps a simpler problem of just trying to sample from the posterior. So behind GLM and LM, there's some type of central limit normal approximation that has to hold. And so Stan, I think, is more capable of fitting a more richer variety of models. So if you're kind of statistically agnostic as to your notion of uncertainty, Bayesian credible intervals are just as good to you as frequentist, asymptotic intervals, then Stan will appeal to you because this one language can code a wider variety of models. If you're more religious, I guess, and the intervals mean something to you, then depending on your application or the point you were trying to make, one software would be more appropriate than the other.
Yeah, I'll just add that if you're writing the actual Stan code, you can also use the packages rstanarm, brms. I'm sure it's invoked in other packages now, but those are two big packages that use Stan under the hood. If you're actually writing your raw Stan code, it's very intuitive. You only need a data model block and parameter block. And so if you have any sense of the math you're using, it's quite straightforward to actually sit down and learn how to code it, which I think is quite nice. If you're using JAGs or older sampling methods, it's fast. I mean, that's how I got into it, as it was like a faster, easier approach to learning a Bayesian language or invoking a Bayesian language. So it's computationally, the sampling chains go really quick, which is nice. But there's lots of new things coming out where sampling goes faster, but this was one of the first big ones, and it does work quite well for that.
Yeah, sorry, and I should say that we're talking about like using HMC, using Stan sampler. You can of course use optimize. You can treat it like a frequentist likelihood, and that will have mixed success depending on the complexity of the model.
Great, thanks. And I guess just to follow up though, yeah, maybe that's sort of the differentiation that could help would be, Stan versus something like Nimble or JAGs or Bugs, where how you sample from the posterior is different, right? And so I don't know if you want to make any comments on that, but I think Lizzie's point is, Stan gets used a lot in the fisheries world as well because it is incredibly fast. The downside is, of course, the way that you do the sort of sampling, you can run into issues with discrete parameters. And so you sort of showed how you can kind of overcome that, which is great. But I don't know if there's any other thoughts you wanted to say there. I think there's a lot of people that use like a Nimble kind of Bugs, JAGs as sort of a way to fit ecological models in a Bayesian framework. So
Yeah, there's benefits and limitations of all software. So I think it's finding for the types of models you fit, finding what works well for your workflow. I think the Stan folks have done, in my opinion, a very good job of creating a workflow that makes it very easy to compare models. Because at the end of the day, that's what you want to do is you want to, science is about competing theories that you test on data. And so it's appealing to be able to fit a richer set of models that correspond, I guess, to a richer set of theories.
Yeah, I'll add one last piece which relates to that, I think, which is that the Stan, I think, has built a nice community, and it's a very interdisciplinary community. So they run a conference most years now that you can go to, and Jonathan Auerbach was there the first year I went. He was talking about, I think, potholes in cities, and there'll be tons of sports forecasts at the meeting, and there'll be ecologists as well. So it has this really nice interdisciplinary community where you can see how your models relate to totally other aspects, and you might get new ideas for how to model biology. I also think it invokes a certain approach to Bayesian at this point, which goes through a very specific workflow, which usually starts with simulating data, fitting your model to real data, simulating from your model, fit to real data. So this real iterative process of predictions via simulation and testing via simulation that I adore. You can do that in certainly lots of other languages, but it will be hammered into you a little bit more, I think, if you enter through Stan. And that has certainly reshaped my biology. Like, I don't think Jonathan and I would have had such an easy exchange about when I came to him, I was like, what the hell is going on with this model if I hadn't walked in with simulated code. So that level of sort of working through the workflow and the type of community you integrate with is different through Stan. It's been great for me, but different things work for different people.
No, that's that's excellent. Thank you. The next sort of top voted question is there an overview paper of different stopped random walked processes in biology?
I have no idea. Maybe. I imagine it's so common. I don't know about this. I couldn't find anything for this problem, like for ecology, this kind of bloom date problem specifically. We were going through the literature at some point, 2019, 2020, and I think various ecologists at the time had realized the inverse relationship. We saw some papers that noted the inverse relationship between temperature and bloom date, like in 1920 or something. And it's kind of crazy to me still how old this field is, how ecology is like one of the oldest sciences that, you guys are looking back, in some cases, hundreds of years. But I don't think, yeah, someone should do a review type paper. Someone writes it, I'll read it.
Yeah, I don't know it either, but I will say Brownian motion is a random walk. So stopping processes are a part of this, but just the random walk is certainly invoked in a lot of null models in biology and evolution. But in terms of stop random walks, I don't know paper, but yeah, I'd read it too.
Excellent. The next one is, do you include priors for the parameters in the Stan models?
I don't think I did. I think they were all the default uniform priors. I guess you always have priors. There's no such thing as no priors, but yeah, you could. It's easy to just add a line. I didn't.
So yeah, so I guess right, there are priors, and then they just like most software now too, right? There's going to be some kind of default that's already in there, and so you can kind of take a look usually and see what the defaults are for each different kind of parameter.
Yeah, I did. Originally I didn't want to use Stan given the audience. I wanted to use BRMS, which I never used before. And I was running into trouble where it has default priors, and it was once I started specifying the variant structure, it started getting mad at me and wasn't fitting well. So again, because I'm not an expert, it's possible I didn't know the magic, the words to say or type. So I do think priors, make a difference. I mean, they're making models. Same with RStan ARM. They're making models, assuming a certain variant structure. If you change it, it might make trouble sampling.
Yeah, in my experience, for the data sets we have here are like really some of the nicer data sets. Like the Martian data set is the longest phenological data set you can get for naturally occurring plants. And the Charrier data, as you probably noticed, is like beautiful experimental data with over 5 treatments of forcing and a whole bunch of previous treatments we included to know the start date fundamentally. So I would say we usually set our priors in Stan, and in messier data, which in my experience is like all other ecological data, then they can become important depending on how complex the model is. So these were nice data sets, I will say, or I think these are nice data sets. So the default priors were easier, probably.
Great, thank you. The next question here is, how do you determine a start date? Is it based on the number of days after a freeze? There was an example of the January 1st start date and the variant start date. When do you choose one option over the other?
So I think Lizzie has the ecological answer to this. That my understanding is that there's some type of similar forcing process called chilling that triggers the start date. She'll clarify. I apologize if I screwed that up. In the code, we just kept it simple by saying it's some unknown parameter that varies. In the experiment, it was the same for all units because the experimenter had forced it to be the same. They made it really cold and then really warm. But in the observational data, it was unknown, falls in normal distribution. That's independent from it's a random effect. It's not correlated with temperature. That may be a bad assumption and could hurt the model.
Yeah, I'll add for the start date biologically, Jonathan got it right. in the early slides where I was talking about endodormancy, yeah, we usually say that plants are exiting endodormancy because they received an accumulation of cool temperatures, and that once they exit that, we would set the start date for forcing. That's the biological story. I do think that the world of leaf out is fascinating because that underlying physiology and that model, which has been fundamentally assumed since the 1970s when it was developed for peaches, is not that well tested. So the walnut data we used, they did try to test that underlying physiological process through a series of additional experiments. But fundamentally, I would say that start date is latent and unobserved in almost all data, and the field doesn't recognize it as latent. They make a ton of unspoken and unwritten assumptions that they are able to model this based on really just what I would say is a series of observations that we really stopped interrogating like 30 to 40 years ago as a field. It's a separate problem, but certainly a big statistical problem for these models.
Great. No, that's an excellent point. And I guess, one of the advantages that you sort of mentioned was Stan, you can kind of facilitate, trying either setting some fixed state based on the biology or, setting that as a latent variable and using it, estimating what that start date is. So great. Here, let me see. I guess this kind of comes back to this, but if bloom date was a distribution rather than a single value, could this also work?
Yeah, bloom date usually is a distribution. I mean, I know I've spent time with Lizzie looking at cherry trees, for example, and what's usually reported is the 75th percentile. Um, Assuming that they're all drawn from the same distribution, you could set the percentile. The bloom date itself is asymptotically normal. The forcing could vary. I'm sorry, I'm thinking out loud. I apologize. The forcing could vary by tree according to, say, a normal distribution, and then you could match over each year you're observing the 50th or 95th percentile or whatever. So yeah, you just have to work it out. So the what I think is given here in the slides is a model for an individual stem or a plant. What was assumed is that we just see in any year, kind of like with the CHAR-A data, independent copies of the same plant. And then with the oak tree data, we kind of ignored the fact that I guess it was 2 or 3 trees. I forget how many trees it was. But yeah, if it was a distribution, you just, I guess, have a normal for each one, and a normal maybe for each bud, something like that. And then now you have a mixture of normals, and then whatever's being reported, the 50th percentile, you could change your model to reflect it. But if the question was, do we account for the fact that it's a bunch of different? No, we don't. We just assume that there's basically one plant, and that plant blooms, and it's we're finding the cumulative sum of one bud or something. But yeah, you can make it more complicated, I guess, to answer that question.
Great. The next question, is it possible to represent competing processes in stopped random walk models? I'm curious about the relationship with survival analysis and competing risks.
Yeah, I think the survival analysis literature comes out of this literature. You see the stopped random literature in the 50s and 60s, and then the survival literature comes out. Similar kind of problems, similar modeling. It's very difficult. I don't know for sure. I haven't thought about it. It's very difficult to model multiple stopped random walks. Going more than the bivariate distribution I think it gets complicated very quickly. So, I guess competing. I guess maybe someone has to clarify the biology. I can say generally bivariate or multiple stopped random walks are hard to model. They rely on multivariate CLTs. And there's the conditions get increasingly complicated. Maybe there was, I don't know if someone wants to clarify, there was like this competing means something more like competing and determining the stopping time, or.
Yeah, I'm not completely sure. It sounds like, though, I mean, you could obviously say you have like different locations and you could sort of evaluate the competing risk by doing those independently. But then what you're saying is if you were trying to model the, multiple stopped random walks at the same time, that gets very complicated very quickly.
Yeah, if there was some correlation among, so you have these partial sums that are correlated across space, it could be very complicated to account for the multivariate distribution of stopping times. Um, but just I would say it's probably equally complicated to have a high dimensional, lots of different survival functions and account. Oftentimes, these models require very heroic independence assumptions, independence across time intervals, that type of stuff. I mean, the original Cox proportional hazard model requires independence across time intervals. Very difficult to fit. People do frailty models, they put in random effects and stuff, but it gets very complicated very quickly.
Great.
I know, Jody, with the rules at the beginning, you can do anything. It's, I want to be uplifting. If you can simulate it from it, you can sample from it. So, sky's the limit.
Great. The last here, I think it's more of a comment, but I just want to make sure I say it here. So you've highlighted phenology of all sorts that could follow the stopped random walks. And then they suggest movement ecology. I guess the question is related to the overview paper of stopped random walks and ecology and evolution. So I think they're sort of asking maybe how else could this be expanded? So just not just thinking about phenology, but maybe thinking about in the context of strictly movement, these stopped random walks be potentially useful in that sort of world.
It's a Lizzie question. I don't know what movement is, so I think that might be a Lizzie question.
I think they're talking about animal movement models where people have observations of collared animals and are watching over time as they move and what causes them to stop. So are they stopping because there's a road or a resource or something else? Not my field. So that was the end of my knowledge there. I do believe they use stopped walk models, but I don't know. I don't know. Hopefully, maybe someone else here knows literature enough to say what they invoke. Like, do they invoke stop random walks or do they invoke some other statistical model when they use it? As Jonathan pointed out, multiple stop random walks are kind of a nightmare. And usually you're trying to add up multiple individuals of caribou or something that you've observed. I guess one takeaway I will have from this talk is that, and I think this is true, I always say this, I think we've moved away from fundamental basic models and seeing how they repeat over time in biology. So I was raised on Nick Catelli's null model book. It feels like, yeah, random walks and stop random walks are ubiquitous in ecology and evolution, but we aren't trained to see them or to notice them or to know how to invoke them or when they're useful as much. So I'll just put another shout out to that would be a great paper if someone would like to write it.
Yeah, I guess I'll just add, just like specifically a CLT for stopped random walks. Under certain situations, like the linear regression hammer works just as well, or even better than the more complicated machine learning method. And is amenable to, is much easier to interpret.
Yeah, and I
Um,
would say this example is I can't see through survival models enough this early in the morning. But we work with survival models for phenology as well. We usually they're a pain, and we usually want something out of them that is that underlying function. So we're usually trying to fit the underlying function that leads to the accumulation to do all the effort to fit a survival model. In this case, the model is really simple. Like we call it a bucket model. The bucket fills up and the bucket has enough warmth so the plant does something. I'm not sure that survival modeling, for example, gives you more when you have a simple model. And the other takeaway I have from this project is I gave you all the complicated biology at the beginning, chilling, photoperiod, forcing. As an ecologist and a plant biologist, we invoked that like crazy, and we still do in my field for the last 10 years to explain this observed declining sensitivity. It might be what's happening. There's data you saw in these figures that isn't easily predicted by the models we have here. On the flip side, the simplest model that invoked no other factors of photoperiod or chilling also explained and predicted declining sensitivities. And I think that's a problem in our field that we needed to do so much to see that the simplest model could also be predictive of a complicated process.
Going back to the survival point, and I apologize if you guys are trying to get through more questions. I mean, this is if you're looking at we're looking at like it's a duration model. We're looking at survive like if the flower survives and until it blooms, then it dies. Under that perspective, then we are doing survival modeling. I was thinking more of like a proportional hazards type model that a different assumption, which is typically like when I think of survival analysis, I think of Cox proportional hazard model. We are modeling the survival of a like you could broadly call the survival modeling, I guess, is my point.
Great. So somebody had asked about the book you just mentioned, and so Jody put that in the chat there. So it is the what was it, Primer of Ecology by Nicholas Cotelli. So is that the one, Lizzie? Or no? Is it the actual No Models book? Sorry, it's the No Models
No
in
Models.
Ecology. Yeah,
Yeah.
yeah, sorry. Um, Great. Well, there's one last question that kind of relates to, I think, what you've already said. But so if bloom date was a function of both cumulative temperature and another predictor variable, for example, nutrients, can we include this in the model to determine how bloom date is controlled between the two?
Yes, but not easily. So the general rule, asterisks, is that if you have cumulative bloom date that's interacting with whatever some other variable, as long as you can derive a central limit theorem for the cumulative sum, then you can get a central limit theorem for the stopping time for the stopped sum. But there's slightly more. So you need the CLT to hold, and then there are additional assumptions you need for the that to translate to a normal approximation on the. So the way I hear the question is, can I assume a normal approximation for the bloom date with some functional form asymptotically? And so anyway, the answer is yes, but you have to make additional assumptions, and those assumptions get more and more complicated the more you complicate the CLT. If that makes sense.
Yeah, if I can add one bit, I would say that sure you can add whatever you want. The beauty of Stan or any of these languages where you fit your own model is you fit your own model. But the other beauty of it that I've taken away from working in this approach and with Jonathan is you could fit the model, and what you very quickly will probably see is that you don't have the data for the inference you want. And I think that's a great take home for the forecasting initiatives as well. And a lot of the work we do is that one of the big benefits of these models isn't that you get to fit the model and see the inference you wanted to see. It's that you often, if you do it well, see that you don't have the data for the inference you want. And then you can push the model and see if you can find predictions under certain experimental conditions that would allow you to differentiate between the multiple models, between the model with just cumulative sum of temperatures versus the model where nutrients have an effect. And I think we don't do enough of this like iterative modeling to determine the experiments we need to differentiate models as well. And so I think adding that to this model and trying to fit it with observed data might not make you feel like you can figure out how much nutrients matter versus forcing, but it might give you the insight if you push the model and push the approach to figure out the critical experiment.
Great. Thank you, Lizzie. That was I think that's a great sort of synopsis and way to think about how we do science. Well, excellent. Well, thank you both so much for the presentation and your time.